Okay, so let's remember what we're going to try to complete the proof of those results that I gave you the last lecture. So we have full branch map, a piecewise C1 possibly with an infinite number of branches, like the Gauss map. You can imagine the Gauss map, but even more complicated. And so there were two. I'm going to start with the result that gives us conditions. So I stated the proposition saying that suppose that F is uniformly expanding and satisfies this condition, sometimes called the Rényi condition, which is that the supremum over all omega in P, so this is omega 1 in P1, and the supremum over all xy in omega 1 of second derivative over the first derivative squared is infinite. Then F has bounded distortion. And bounded distortion means that there exists K such that log of the Fnx over the Fny less than equal to K Fnx minus Fny, which in particular it means this is bounded by K, okay, for all n greater than or equal to 1, all omega n in Pn, and all xy in omega n. So one difference between the assumptions and the conclusions of this result is that the assumptions apply, in principle, you can verify them just with one iterate of the map, right, by looking at the map. If, for example, if the derivative is bigger than 1 everywhere, that's just a condition that you can look at the map, the derivative is bigger than 1 everywhere, then it's uniformly expanding. And this, you just, if you have, of course, you need to have some information about the map, but this just depends on the map. You don't need to iterate the map, right? So, for example, for the Gauss map, we can check these two conditions, right? Whereas it's highly non-trivial to check this condition because this condition is a condition that says that for any n, you need to look at Fn, you need to look at the element of n, of the partition Pn, you need to look at 2 points, and you need to compare the derivative at these 2 points and show that it satisfies this condition, right? This is really non-trivial, this. So it is also non-trivial to show that this implies this, okay? It's not, as we shall see, it's not a complicated calculation, but that's what I want to do first today. Are there any questions about this? So then afterwards, or if you remember, we already proved that what we're interested, the reason we are interested in this bounded distortion property is, so first of all, sorry, let me also mention again that this is a generalization of the piecewise affine case, right? If you have a piecewise affine case, both of these conditions are automatically satisfied, right? If you have a unit interval and you have at least two branches, then both of these branches must have derivative bigger than 1, and they have constant derivative. So on each branch, the second derivative is 0. Right? So both of these conditions are satisfied, but also independently of these conditions, in that case, it's also easy to show that this is satisfied, because also here, every iterate is piecewise affine. So if you take 2 points inside the same branch, the derivative will be the same. So this will be equal to 1, so this is be equal to 0. So anyway, this is satisfied, right? So both the bounded distortion is automatically satisfied. Also, these conditions are automatically satisfied in that case. But this is much more general, of course. And then last time, we tried to understand exactly what this bounded distortion condition means. Remember that intuitively, this means that the ratios between sets is preserved, right? So just one comment about the intuitive meaning of this. Remember that every interval omega n is mapped to the whole interval 0, 1, let's say to the whole interval, right? And if you remember, we proved the lemma, which is important to keep in mind, because this is a very formal statement, right? But when you have a visualize the meaning of this bounded distortion, it means that if you take any subinterval, or in fact, it doesn't even need to be a subinterval, it just needs to be some subset of positive measure here, and you look at its image here, right? Then the ratio between the measure of A and the measure of this interval is roughly the same as the measure between the ratio between Fn of A and the whole unit interval, right? This is why it's called bounded distortion, right? If the map is piecewise affine, then you preserve this ratio exactly. If A is, the measure of A is 1/3 of the interval, then its image will be exactly 1/3 of the image, right? Bounded distortion said that it is bounded above and below by a constant independent of n, right? Because the constant depends only on this. So even when you take very large iterates, right, so that you have very small intervals stretched very, very much, then if you take an interval that is here or here or here, it doesn't matter where you take the interval, when you look at its image, the ratio between these two will be uniformly bounded. This is the intuitive idea behind bounded distortion. And bounded distortion has a lot of consequences. We proved last time that it implies that Lebesgue measure is ergodic. And we will show today the most important of all consequences of bounded distortion, that there exists an absolutely continuous invariant ergodic measure for this full branch map, right? So that is really the most important consequence, the actual existence of a physical measure. So there's two results we want to prove today. First this, and then the existence of physical measures. So how do we prove this result here? So we will have 3 steps. The first one I will not do in detail, actually, so. So there is, I will write it as 3 lemmas. So this is under the assumptions of this proposition, right? So this is just a very simple statement. We have so there exists a K, so here, there exists some K. It's not really the same K as here, but it doesn't matter. There exists a K such that this is K f of x minus f of y. So you see intuitively what you're saying when x is equal to y, this is 0, right? When x is equal to y, this ratio is 1, so this is also 0. So when x is very close to y, then f of x is also very close to y. It's giving you a kind of uniform bound. Again, the point about this is that this constant does not depend on which partition element. So the constant for every partition element, you have this kind of, it's a kind of Lipschitz bound in some sense on the derivative at nearby points. So this is a little technical statement, and the proof is very simple using the mean value theorem. So I think I will leave you. There's nothing much interesting. You can look at the notes. You can easily do it yourself, actually. Use the mean value theorem on the first and second derivative, assuming this condition here. In fact, this lemma does not need the uniform expansion. It's just a direct consequence of this. So I think I will leave that because the other two lemmas instead have some more conceptual and interesting calculations. So I think it's better to spend the time doing that. So here we have the following. We have that for all, again, for all n. This is for all n greater than or equal to 1, and for all omega n in Pn, for all xy in omega n, we have that the log so this is what we're trying to bound. The ratio between these derivatives. And the first step, there's two steps really in the proof, is that this is less than or equal to this constant, the same constant here actually, times the sum I equals 1 to n of fi of x minus fi of y. So let's see the proof, and then we will discuss what we do with this, right? What this is saying is that you can basically take, so we take our interval xy inside omega n, right? And then we iterate it once, and we have f of x, f of y, right? And then so on up to fn of x, fn of y. And we take the sum of all these sizes, right? We're looking at the images. This here, xy is an interval. Xy are 2 points in here. So you take the interval xy, and you take the images. It's an interval. You take the images, and you take the sum. So it's very interesting. Well, it's very interesting. It's curious that we get that. It's also not obvious immediately how this is going to help us get a uniform bound, right? Because when n is very big, you are summing lots of terms, but we shall see that in the next step. First of all, let's do this calculation. And this is just a one-line calculation, but it's a calculation that is quite classical distortion calculation in some sense. So I think it's worth doing this step to see also what properties of the map we use here. So it's really almost just all algebraic manipulation. So we have here log of dfn of x over dfn of y. So in situations like this, the first thing you do is you use the chain rule, right? So we can write this as each of these is the product, right? Remember, by the chain rule, we have the dfn of x is just the product of the derivatives along the orbit of x, right? So this is just the derivative at x times the derivative at f of x times the derivative at fn minus 1 of x. Exactly. Yes, I think I did not see. I think you've got the idea. I think that's precisely it, what you said. So let me write it out in detail. So this is just by the chain rule, we write this as a product, right? So this is just I n minus 1. And then here we have f prime in fi of x. And then here we have f prime in fi of y, right? And then this we can write as the sum of the logs of the same thing, f prime fi of x, f prime fi of y. And then here we can just do a little bit of manipulation here, and we get that this is equal to the sum I equals 0 to n minus 1. And then you can check, we can easily write this as the log of f prime fi of x minus f prime of fi of y over f prime of fi of y plus 1. And then you can we can put some we can put the absolute values inside. So we can put the absolute values here. And then a standard property of the log, right? So then this is positive once we put the absolute values inside. So I guess we need to put a less than or equal to here. So once we put the absolute values inside, this is positive plus 1. So the log, sorry? Exactly, we can drop the logarithm because the log of 1 plus x is always less than or equal to x. So we can write this as the sum of I equals 0 to n minus 1 of just what's inside here, f prime fi of x minus f prime fi of y over f prime fi of y. And this we can just write as less than or equal to the sum I equals 0 to n minus 1. Yeah. Okay. So here we kind of separate out this sum, so we get this will be minus 1 here, so we get f prime of fi of x over f prime of fi of y minus 1. And then we apply this. Right? That's why we wanted this. And this is just less than or equal to k times the sum I equals 0 to n minus 1 of fi of x minus fi of y. So there's nothing, we haven't really used anything here, except for this lemma here. Okay, so this is really just an expansion. This lemma here just shows that you can, just using the chain rule, you can really write this distortion term as the sum. I mean, the proof doesn't use anything really substantial, but it shows something kind of not necessarily expected, that you can bound this by the sum of these terms here, right? We have not used the uniform expansivity yet in the theorem. We've just used this condition here to get lemma 1. In lemma 2, we haven't even used this condition. We've just used the conclusions of lemma 1 to get this. And now the question is, how do we bound this? How do we get a uniform bound for this, right? Because what we have now is that this bound, but what we want is this bounded by fn of x minus fn of y. We want this bound, which is less than or equal to 1. Right? So in particular, we want this to be uniformly bounded. However, the problem is independently of n. Right? The problem is that if n is big, there are lots of terms here, right? Not only there are lots of terms, but these terms, are they increasing or decreasing with n? They're increasing. The size is increasing, right? Because these intervals, they're small. This is uniformly expanding, and it's getting bigger and bigger and bigger and bigger. So we have a sum of increasing terms. When n is very big, you will get more and more terms. So how do we get this sum to be uniformly bounded independently of n? What do you think? Is it possible that this sum is uniformly bounded independently of n? Let's see if we can have a kind of intuitive argument before we write out the calculation. Ling, do you have some idea? let's have a intuitive, a heuristic argument before we look at the calculation. How is it possible that you have an infinite sum of increasing terms, more and more terms, uniformly bounded? The derivative is bounded from below, for sure, yes. Below, but not above.
So 1 over is bounded above.
1 over the derivative.
Yes, 1 over derivative bounded above.
1 over the derivative is bounded above, yes.
So we can.
No, the second derivative does not need to be bounded above in this situation. Because you can have, so remember that this is piecewise, so the, no, 1 over the first, but anyway, I don't know what this would, what would help. But since you're mentioning, remember that this is maybe an infinite partition, right? So you may have some elements of the partition that are very small. And in these elements of this partition, this is not bounded above. So you may have, this may be arbitrarily large, but because the derivative is also large, then this is bounded. So both of these may be arbitrarily large, but the ratio is bounded. But you're thinking in the right direction when you're thinking of the derivative, because this is what we need to use, the uniformly expanding property, right? We have not used the uniformly expanding property. But the uniformly expanding property seems to go in the opposite direction of what we want, right? The uniformly expanding property is telling us that this is growing exponentially fast. Exactly. Exactly. So the heuristic argument, which is very simple, which we can write down, but it's very simple, is that I was trying to fool you, right? I tried to confuse you. Huh?
For instance, we write n minus 2.
It's okay, it's okay. I think you got the idea. Let me try to.
And by the mean value, we have after that we can denominator. In the denominator.
Okay, I think you're saying the right thing, I mean, Moksin. So the point is the following, is that it's true that these are exponentially growing, right? But it's also true that the last term is bounded, right? Toluwani, what's the bound for this last interval here, for the size of this interval here? Is less than equal to what? Excuse me? Exactly, the size of the interval, right? So, the fact that this uniformly expanding map means that this is exponentially large compared to this one, for example, or compared to this. But it also means that this is exponentially small compared to this. Right? So it can go both ways. So this uniform expansion means that if you take a little interval, then it is growing exponentially fast by the mean value theorem. But we know that at the end, it will land in something that is less than 1, and it lands bijectively, diffeomorphically, right? So this means that this one is exponentially small. So this means that if you have very large n, it's true that you're adding lots of terms. But all these terms are exponentially small, right? So this, if you start with this, and then the previous term will be exponentially small with respect to this, and the previous one and the previous one. So all these terms are exponentially small. So when you go backwards, you have a converging geometric series, which is probably what Milmukhin wrote on his paper, right? So let me write this argument, which I think is probably what you have, Milmukhin, right? So that we have this conclusion. Lemma is, of course, is that the sum I equals 0 to n minus 1 of fi of x minus fi of y is less than equal, I will use this just to say less than equal to up to some constant, fn x minus fn y. Right? And the proof is simply this. This proof is that by uniform expansivity, since f is uniformly expanding, we have here fi, so we have here xy, then we have at some point fi of x, fi of y, and then we have fn minus I that takes us all the way to fn of x, fn of y, right? And the mean value theorem tells us that the ratio, so fn of x minus fn of y, is greater than or equal to the derivative dfn minus I in some point xi, so there is some point xi times fi of x minus fi of y, right? And this derivative is greater than or equal to c lambda So did I use lambda as an exponent or as a... So I can't remember if I took lambda bigger than 1 or lambda bigger than 0, and I put lambda in the exponent. Anyway, let's write it like this, lambda bigger than 1. Or did I write e to the lambda n? Which notation did I use first for the definition of uniformly expanding? Exponential. Sorry? Lambda to the power n is what I use. Sometimes I use one notation, so I take lambda bigger than 1 and takes lambda to the power n, fi of x minus fi of y. Okay, you agree? This is simple. So this is the definition of uniformly expanding, is that every point satisfies the derivative, satisfies this, right? And this means that this is the expansion you have here. And of course now this means that we can reverse. So this means that fi of x minus fi of y is less than or equal to c to the minus 1 lambda to the minus n fn over x minus fn of y. Okay? Minus I, thank you, yes. Yes. So I think this is probably the calculation that, the idea that you had, Mokshin, right? So, okay, so this shows simply the heuristic fact that these intervals here are exponentially, that's what I said about them being exponentially decreasing in size in terms of this, right? So what this captures is so then this is obvious, right? So then this implies that the sum here, the sum of fix minus iy, so the sum I equals 0 to n minus 1 of fix minus fi of y is less than or equal to the sum I equals 0 n minus 1 of c minus 1 lambda to the minus n fnx minus fny, right? And so this no longer depends on I, so it's really just the sum of these. Sorry, I keep putting n here, minus I, right? And so this is less than or equal to just the sum. We can now take the infinite sum, actually. So this is just less than or equal to the infinite sum. So this is just 1 over c, the sum from I equals 0 to infinity of lambda to the minus I. Okay, this is now our constant, fn of x minus fn of y. So the trick here, if you want, not the trick, but I kind of tried to emphasize what looked initially like a paradox in the lemma, but it's not, is that when we say that this sum is bounded by this, so when we yes, so when we get that this is bounded by this sum, right, and I emphasize the fact that these are all increasing, these terms, and so how can you get a bound that is independent of n, right? The reason you get a bound independent of n is because there is a hidden dependence of n of the interval, right? So it's true that this bound is independent of n, right? But when you take very n large, then you're taking omega n in Pn, and you're applying this to the points in omega n, right? So when you take n very large, you're actually taking omega n in Pn, which means you're taking omega n very small, right? And therefore, when you take the sum, you take 2 points, so you're starting with something that is extremely small. Right? The bigger n you take, and the smaller you start with, and it's exponentially small in n. So it means that when you sum all these iterates, they still give something uniformly bounded, right? Which is what you see exactly in this calculation here. So all of these are exponentially small in terms of that. So you can sum all of these, and these are uniformly bounded because this sum here is bounded by the infinite sum. It's a geometric backward geometric series. And so it doesn't matter. So this constant now is independent of n, because this is bounded by the infinite series here. So this completes the proof of this proposition here. So we've used this condition here to get lemma 1. This is a very elementary, you can think of it almost as a regularity condition. And then we've used the uniform expansivity to get this uniform bound for the sum. This uniform expansivity is actually very important in this case. You cannot, if you take maps that are not uniformly expanding, you may fail. You cannot get those uniform bounds like that. So you can actually fail to get the bounded distortion. In fact, let me just give a quick example. Yes, let me give a quick example of a full branch map that fails. I think maybe I gave this already in the, maybe in one of the exercises, I'm not sure. So this is example, in fact, it's a counterexample. Consider the map f of x equals x plus x squared mod 1. What does this map look like? So the derivative of this map is 1 plus 2x. So this is quite easy to see that this is a two-branch. It's a full branch map. There is some point here. Okay, I will let you think about it a little bit on your own, but you can easily see that it's got two branches. There is some point between 0 and 1 such that this maps, these are two branches. But here, the derivative, you see, is always bigger than 1, except at the point 1. At the point 0, sorry, when x is equal to 0. So when x equals 0, the derivative is 1, right? And the derivative is something like this. When x equals 1, the derivative is 3, right? So the derivative is monotonically increasing between 1 and 3 here. And here the derivative is 1, which means that this is tangent to the diagonal, this point, right? This is a very interesting example. There's a lot of research on this kind of map. In fact, Mubarak, PhD student here, Mubarak is doing his PhD on some generalizations of these maps. And because it is almost uniformly expanding. So can you tell me why it's not uniformly expanding, this map? Exactly, at 0 is 1, right? So if you take the orbit of 0, 0 is a fixed point, so the derivative will always be 1. Well, even if we avoid 1, it turns out, okay, it's not immediately obvious, but it's still not uniformly expanding because you can come arbitrarily close to 1. So So it's not uniformly expanding. But what we're most interested in here is whether it has bounded distortion or not. So I don't think I want to spend too much time on this, but I want to show you an example, a simple example of a full branch map, which is almost uniformly expanding, okay? Which presumably will also, clearly also satisfies this condition here, because the first and second derivatives are uniformly bounded, so this is clearly satisfied, but it's not uniformly expanding just about, okay, just because of this point here. And how can we easily see that it is not uniformly expanding? So what will the nth iterate look like when we have f to the n? So again, I don't want to do a full proof here, okay? I'm just going to show you heuristically, and then maybe you can check that this is really correct. But it's going to have lots of branches, right? So Fn has 2 to the n branches, because it's full branch, you can easily check. So here you have, you chop each one in half, and you just get your 2 to the n branches, right? And so you're going to get lots of branches here. These branches are going to be all very steep, a big derivative, okay? And what about this branch here, this last branch, so this first branch? Okay, so this first branch is going to map to the whole interval, right? So do we have bounded distortion? So what's going to be the derivative at the fixed point here of this branch? It is still 1. The derivative at the fixed point is always going to be 1, right? Because it doesn't matter how many iterates you take, the derivative at the fixed point is always 1. If it's 1, it's just by the chain rule, it's just the product of 1, so it's still 1. Okay? So usually, if you have a fixed point, if the derivative is 2, then the derivative of the second iterate of the map at that fixed point is 4. Right? So the derivative, you multiply the derivatives by the chain rule. Here also you multiply the derivatives, but because it's 1, it stays 1. Right? So this means that we have this branch here, and we have the derivative, it's still 1, but since when n is very large, you're still mapping a very small interval to the whole interval, you must have points where the derivative is very large, right? By the mean value theorem, you must have some point where the derivative is the ratio between this and this. So there must be some points where you have very large derivative, right? So this means that if you take the ratio between the derivative at 2 points in the interval, this cannot be uniformly bounded, right? Because here you will have 1 point where the derivative is 1 or arbitrarily close to 1, and then you must have some other points that are arbitrarily close where the derivative is huge. And if you take n bigger, you will get even smaller and smaller, but the derivative here is always 1, but there must be some points where you can make the derivative bigger and bigger and bigger. The bigger you take n, the smaller this will be, and so the bigger the derivative you will have somewhere here. Okay, so this is a very nice and very simple example that helps to show really to what extent these assumptions are, that it's, they're not necessarily necessary. I mean, there may be examples that don't satisfy this, which still satisfy bounded distortion, but you cannot just remove, for example, this uniform expansivity assumption, right? It's used in that part of the lemma, and as you can see, the conclusions fails, right? And in fact, in this example, also the conclusion about the existence of a absolutely continuous invariant ergodic measure also fails. So the next theorem we're going to prove is that under these assumptions, there exists an absolutely continuous invariant probability measure fails. And what happens in this case is very interesting because this is topologically conjugate to 2x mod 1. So it turns out, again, in our discussion of topological conjugacy, I think we use the fact that both of them should be uniformly expanding. I can't remember, but it's easy to see that that does not fail. You can still show that this is topologically conjugate to 2x mod 1. In that particular argument, this is not a problem, but even so this means that it has many points that have dense orbits and so on. But it turns out that in this particular case, it has a physical measure, but the physical measure is the delta Dirac at 0. So most points, they move around, but they come very close, and they spend a lot of time here, and then they move away, and then they spend very close. So this is why this is such an interesting example, because it is just on the boundary of all these uniformly expanding full branch maps that we've been studying. And it shows that if you just push the assumptions a little bit beyond what we have, then you may have a completely different situation. Okay. So what's left, indeed, is to prove this last statement, is that if we have these conditions here, in fact, we will prove that if we have bounded distortion, then we have an absolutely continuous invariant probability measure, and it does not hold in this case here. Everything okay with you guys at home? Yeah? Okay, so what do we want to prove here? So the final result, theorem, okay, F piecewise C1, bounded distortion, so full branch, bounded distortion implies there exists unique mu absolutely continuous with respect to Lebesgue invariant probability measure. And because it is absolutely continuous, and because we know that Lebesgue measure is ergodic, then this is automatically also ergodic. So the reason this is interesting is also because we now need to construct an invariant measure. So we have constructed invariant measures before. Do you remember how we constructed invariant measures? So we have the sequence Remember, we already have studied these sequences before. But when we studied them before, we assumed that F was a continuous map. And we assumed that the space was compact. We use this to show that if you have a continuous map on a compact metric space, then there always exists some invariant measure by showing that every weak star limit. So it's easy to show that each of these is a probability measure. And then we showed, remember, one of the results at the beginning was that motivated a lot of the definitions was that every weak star limit point was invariant. However, here we want to apply this in a more general setting. We want infinitely many branches, so we don't want to assume continuity of the map. We don't really even want to assume compactness. We're not going to use abstract results. We're going to use the properties, more detailed properties of these maps, okay? But the main idea is the same. We're still going to look at limit points of this. We're going to show that limit points exist. We're going to show that the limit point is absolutely continuous and invariant, right? That's the philosophy here. So one interesting thing is the absolute continuity. So notice that each mu n is absolutely continuous, right? Notice that mu n is absolutely continuous with respect to Lebesgue because f star, since f star I Lebesgue of some set A, right, is by definition the Lebesgue measure of f minus I of A, right? And this map is piecewise C1, right? So when you take the pre-image, so each branch is a C1 diffeomorphism, right? Which means that if you take the pre-image of a set with zero Lebesgue measure, it will also have zero Lebesgue measure, right? Because we have here, we have this piecewise map. Here we have some set A. Here we have, even if the set is very crazy, because this is a C1 diffeomorphism, the pre-image of a set with zero Lebesgue measure must have zero Lebesgue measure, right? So, so this means that each of these is absolutely continuous. So does that mean that a limit point will also be absolutely continuous? Do we get the absolute continuity for free? Let's look at an example, a very nice kind of detailed example where we can do this calculation exactly. So take the map f of x equals 1/2 of x. Simplest possible map, right? So what do these maps, what do these measures look like? So let's say, what does f star of Lebesgue? For this map. So we take Lebesgue measure here. Now we want f star of Lebesgue. What's going to be the measure of this set here for f star of Lebesgue? And what's going to be the measure of this set here for f star of Lebesgue? Well, what's the definition of f star of Lebesgue? F star of Lebesgue is equal to the Lebesgue measure of f minus 1 of A. Two times, for which map? So here we have 1/2, right? So if I take a set here, the pre-image is empty, right? So this means if I take here 1/2, so if I take any interval in 1/2 1, and I take the pre-image of A, this will be empty, so it will have Lebesgue measure 0 if I is contained in 1/2 1. Whereas if I take a set here, A, yes, if I take this set here, right, so if A belongs to 0, 1/2, then the Lebesgue measure of the pre-image of A will be twice as big, right? So it will be equal to 2 times. Let me use this notation for just the Lebesgue measure of A. 2 times on 0, 1/2. Is that clear for everybody? Yes? So this means that this measure, f star of Lebesgue, is living on the interval 0, 1/2. It only gives positive measure to the interval 0, 1/2. And it's a kind of renormalized Lebesgue measure. So it's kind of every set for that measure has its measure is twice what its Lebesgue measure is. And so you can continue this. You can, sorry, I don't know why I put f star. I went f star here. So you can easily see that f star 2 of Lebesgue measure of A, right, is equal to Lebesgue measure of f minus 2 of A. And what's that going to do? Exactly. So you can see that I will let you do this, properly because time is running out actually. So it turns out that it gives 0 measure to the interval 0, 1/4, 1, and is equal to 4 times the Lebesgue measure of A if A is in 0, 1/4. Okay? And it turns out that you can easily see that you can generalize this, right? So you have a sequence of measures. Each one is a probability measure, right? Because if you plug in this interval into here, you get 1, right? So the measure of the whole space is always 1. These are probability measures. But these probability measures are living in a smaller and smaller interval containing 0, and they have larger and larger density, it's called, right? So this is the density with respect to Lebesgue. So we let Hn, since these are absolutely continuous, then we let H be what's called the Radon-Nikodym derivative, or the density. Every measure that is absolutely continuous with respect to another has a density, right? What this means is that mu n of any set A is equal to the integral of A of Hn with respect to d Lebesgue, m, okay, Lebesgue. This is what, so the Radon-Nikodym theorem is a theorem in measure theory that tells you that every measure that is absolutely continuous has a density, and the density means that you can write this measure as an integral in this sense of this function, right? So these densities here are exactly this. So this here, in this case, the density of this measure with respect to Lebesgue is 0 here, and it's 2 here. The density of this one is 0 here, and it's 4 here, right? So in this particular example, the density Hn is a step function. It's a simple step function that on the interval 1 over n has size 2 to the n, right? And is 0 everywhere else. Exactly, the characteristic function of that. So what is the limit, the weak star limit of these probability measures? Here we have a sequence of probability measures. We have f n star of Lebesgue. So you can see and you can check that the weak star limit is the Dirac delta in 0, clearly, right? Because if you take any interval that does not contain 0, sooner or later that will have 0 measure, right? Because the sequence of measures is in smaller and smaller neighborhoods of 0. So if you take anything that is outside 0, sooner or later it will have 0 measure. So the only measure that this is converging to here, even if you take the averages of these, is the Dirac delta at 0. Excuse me? Exactly. Exactly. So the reason for this example is to show you, this is something that is known. I mean, show you in a very concrete case how the limit, weak star limit, of a sequence of measures that is absolutely continuous is not necessarily absolutely continuous. Right? So even though it would be too easy, life would be too easy otherwise, right? Because otherwise, it's like we would always have absolutely continuous measures because, okay, we have not shown that this is invariant, but you can believe from what we've done before that probably the limit of this will be invariant, and we will show that it is. If it is also automatically absolutely continuous, then we have not used any properties of the map, right? It's just automatic. Instead, it is not. As you can see from this map, this sequence of densities here does not converge to a density, right? This does not converge to a density. This is a sequence of measures that just converges to the Dirac delta 0. So we need to show, the reason why I gave you this example is to emphasize the fact that we have this sequence, but also to motivate, in some sense, what is happening is that these densities Hn, they're unbounded, right? Since each of these is actually a probability measure, and each one of these has a density, right? The only way you can get this density, and the integral of this density on the whole space is always equal to 1, because they're all probability measures. So the area, if you want, under the graph of this density has to be equal to 1, right? So the only way you can get intuitively, this is not a formal proof, but the only way you can get these measures to squeeze into smaller and smaller subsets is by letting the height of these go to infinity, right? So intuitively, maybe what we want to do is to show if you have a bound for the density, then maybe it will stop this density from blowing up and having a situation like this, right? Because if you say, okay, the density has to be uniformly bounded, then in some sense you cannot squeeze the support of the measure in very small regions, because if you did that, the density would have to be big, because the integral has to be 1. So that's what we're going to do. Okay, so the main proposition there exists a constant k under the assumptions of the theorem such that infimum over all n and x of Hn of x, the supremum of Hn of x are bounded. And for all n and xy in the interval I, we have that Hn of x minus Hn of y is less than equal this constant Hn of x times the distance between x and y, which in particular is therefore less than equal k squared times the distance between x and y. So this just says that these densities are uniformly bounded above, right? So for every n and for every x, this is greater than equal to k, less than equal to k. In fact, I'm not quite sure why I wrote this. This is obvious. I think this is the main property, but also it's Lipschitz, right? So also this is saying that each of these densities is Lipschitz, which is not obvious at all. Our example is not Lipschitz, it's discontinuous, right? In our example, it's a step function like this. So this is Lipschitz with a uniform Lipschitz constant that does not depend on n. And this implies the theorem. So let's, before we prove this, let's show that this implies the theorem. Sorry? Exactly. So what we have is an equicontinuous family. Uniform Lipschitz constant, uniform bound. So by Azzela-Ascoli result, right? So we have this family Hn is equicontinuous, bounded and equicontinuous. So this means that there exists some subsequence, right? So by Ascoli-Azzela, which is a standard theorem in function analysis. It means that we can find a converging subsequence to another function that satisfies the same condition, right? So it's kind of saying that these conditions, this bounded and equicontinuous implies that this family is, can't remember what the terminology is. Anyway, any limit point will also satisfy the same conditions, right? And there exists limit points. So there exists some h and j converging to h, okay, satisfying the same conditions, also bounded and Lipschitz. Yes? Yes. And therefore, we can define a measure. We can define a measure with this h, right? We have here an h, which is, oh, I guess, this is why I wrote it, because this is bounded away from 0. Sorry. This is what we wanted, is that simply it is positive everywhere, okay? In fact, this Lipschitz function is bounded away from 0. Yeah. But that's not so important, but it is strictly positive, which is different from the example we had there, right? And so now we can define mu, define a measure mu, to be defined by having H as a density. And we claim that this is the measure we want, right? So strictly speaking, we've not directly looked at the limit point, the weak star limit point of this point. We've taken a little bit of a stronger kind of limit. We've looked at the densities, right? And then using the fact that the densities are all have these uniform bounds and uniform Lipschitz, we take a limit of the densities, right? And then we fix the density, and then we use that density to define a measure. And I'm a little bit worried about the time that we've got, so I think I will leave it for you to look at the notes. It's only 2 lines to show that mu A is so this is automatically absolutely continuous, right? So we're looking for a measure that is invariant and absolutely continuous. So this is automatically absolutely continuous by definition, because if we have a map of this kind, if you take a set of 0 Lebesgue measure, then it must have 0 measure. So this mu is absolutely continuous with respect to Lebesgue. And then it's just really just checking using the definition. It's a couple of lines which in the notes, and we can show that mu is invariant. Okay, I will let you do that. So the whole proof boils down to studying these properties of these densities here. So what are the steps? Okay, so to prove these densities, we will do something very interesting, which we will have almost an explicit form for these densities. So the lemma is this, is that Hn is actually of the form 1 over n, the sum I equals 0 to n minus 1 of Sn, where Sn is equal to, Si, where Si of x is equal to the sum of y in f minus I of x of 1 over the derivative dfi of y. So what we're saying, and also we have that this Si is the density. So Si is actually the density of Fi star of Lebesgue, right? So okay. So this is just the sum. So this is just really, the main result is this, is that Si, the density of F star I of Lebesgue is given by this, okay? And then it follows almost immediately that Hn is given by this. But this is the key point. This is a non-trivial statement. This is what we need to show. What is this saying, though? It's not as strange as it seems, right? What it is saying is that, in some sense, there's a relation. So, okay, we have, this is Fi. This is the map Fi, so it should have many branches actually, but this is the map Fi. We have the map Fi star of Lebesgue, and it turns out that the density of this measure is given by at the point x. So the point x is actually here. Let's say this is the point x, right? But, so the density is actually on the interval here. You look at the point x, and the point x is given by looking at all the pre-images of x. These are the pre-images of x. And looking at the derivative, 1 over the derivative here. Okay, at the moment, it's not clear why this should be the case, but as you can get some idea of, as we do the calculation, why it should be the case. But this is a very explicit, this is a remarkably explicit formula for the density of this measure. Right? And let's say that intuitively, I don't know how I should say what is the intuitive reason, but the derivative at these points are telling you whether the Lebesgue measure is kind of contracted or expanded, right? If you take a little neighborhood, whether the Lebesgue measure of a small interval here and its image, whether the Lebesgue measure increases or decreases, right? We're trying to construct a measure that is invariant. And remember, when you looked at the invariant measure, it means that if you take a little interval here, and then you take the sum of all its components, they should have the same measure of that, right? This does not really explain why that is, but maybe we can see it from the calculation. So we'll try to do 2 steps of the proof. I will leave you to fill in some of the details. But, so this is the part that we need to prove mostly. And so I'm going to do it like this. So remember that we have some interval omega n that maps maybe I should call it I, it doesn't matter, I, Fi, maps to the whole interval 0, 1. And here we have so if we have a set A here, and then here we have the set F minus n of A intersection omega I. Then, by the standard calculus, we have that the measure of A, so the Lebesgue measure of A, is given by integrating over this set here, F minus n of A intersection omega, integrating the derivative df of I with respect to Lebesgue. So this is Lebesgue measure. Okay, this is just, what is it? Fundamental theorem of calculus, I think. So the way the measure, it's a kind of generalization of the mean value theorem, right? So the way the measure maps, the way the map maps a set of positive measure is that it maps it to a measure that is given exactly by taking the integral of the derivative. Right? At each point, infinitesimally, the measure is stretched or contracted. And okay. And similarly, you can go backwards in this, and if you go backwards, you will see, if you think about it a little bit, you can take the derivative backwards, and so you get that the measure of f minus n of a intersection omega is equal to the integral of a of 1 over dfi in f minus I of x intersection omega. Okay, so this is again Lebesgue. Okay, this is not completely immediate. You have to kind of think about it. It's just the same result but going backwards, right? So estimating, starting from A, you take the inverse and you get this. And the reason we have this is because then we immediately get F star I Lebesgue of A is just equal to, by definition, Lebesgue of F minus I of A. And this is equal, by definition, the sum over all omega I in Pi of the Lebesgue measure of F minus I of A intersection omega I, right? Because F minus I of A has many components, right? Each one in each branch. So if you want the Lebesgue measure of this, you just sum the intersection of this preimage with each branch. And then we use this here that tells us that this is exactly the integral of A of 1 over dfi in f minus I of x intersection omega, the Lebesgue, the sum of all omega I in Pi, right? And now these are all disjoint intervals, so this can go inside, the sum can go inside the integral. So this is actually the sum, the integral over A of the sum over omega I in Pi of this thing. And this, if you think about what this is just at this point, once you fix the omega I, this is just equal to the integral of A of the sum over all y in the pre-image of x, right? Because when you sum over all partition elements, and for each partition element you take f minus I of x intersected with that partition element, you get exactly just all the possible pre-images of x, right? Because x has exactly one pre-images inside each interval omega I. So this is exactly just the integral of the sum over all the pre-images of 1 over the derivative of fi in this pre-image, right? So this is just exactly what we wanted, which is integral of dfi in y, right? And this is exactly integral of A of si the Lebesgue, okay, which is exactly what we wanted to prove. So this shows that this is exactly the form of this, okay? So we've just used the fact that this is a full branch C1, piecewise C1 map, because we just used this calculus formula, right? All we've used is the fact that you can estimate the way these measures transfer by using the derivative. So, okay, we finished. I just want 5 more minutes, if you don't mind, and I will just give the key. So at this point, it's easy to see that since this is just the average of the SI, it's enough to prove the corresponding statement for SI, right? If SI is uniformly bounded and Lipschitz continuous, we will get exactly the same thing for Hn. So really what we need to do is to prove that those bounds for Si. And I will just do one step. okay? So the lemma, final lemma, is that Si is uniformly bounded and Lipschitz as above, okay? And I will just give you a heuristic idea of the why it's uniformly bounded, right? So the Lipschitz is, you can see in the notes, is just a couple of extra lines. But since we've run out of time, so why is it uniformly bounded? Well, that is fairly easy, right? Why is this uniformly bounded? So if you remember the exercise to show that every piecewise affine map the Lebesgue measure is invariant, it's very similar to that argument here, right? So although here we want to use the bounded distortion results. So let me call it Sn, just as the same, so it's just easier. So we have our intervals omega n, we have Fn, we have that it maps to the interval 0, 1, right? And then by the bounded distortion, implies that, you know, the df n of x over df and y is, well, let me write it also since we are very quickly. Basically, it means that the derivative is roughly the same at every 2 points, at every point in omega n. That's what the bounded distortion says. The bounded distortion says that the ratio between the derivatives, the log of the ratio between the derivatives is bounded, which means that up to some constants, they have roughly comparable derivative, right? Where the constants that are hidden inside here are independent of n, right? This is the key. In fact, this is really the key heuristic important consequence of bounded distortion. And so what this means is that you can think of the distortion of the derivative as being constant, more or less, right? So this means that since this maps to the interval 0, 1, this means that roughly, so this means that if you look at the size of omega n, okay, times the derivative Fn of some psi n here, you know, using the mean value theorem also, this will be roughly 1, right? Which is the size, the Lebesgue measure of the whole interval, if the interval is 1, right? And because the derivative at every point is more or less the same, right, then this is kind of a value that roughly just depends on this. And so this means that omega n, that dfn, is roughly of the order of 1 over omega n, right? So the fact that you have bounded distortion tells you that the derivative inside this branch is roughly the same at every point. And if it's roughly the same, then it must be roughly 1 over the size of the interval, right? Because that's what the derivative needs to be, because this interval is of a certain size. It maps to some uniform size 0, 1 with bounded distortion. So the derivative is roughly the same at every point. And then we're done, right? And then we have, so this implies that the sum of 1 over dfn of psi n for overall omega n in Pn, right? Because we take for each interval omega n in Pn, we have this. So for each interval omega n, we take 1 over this, which is what we're trying to estimate, right? This is basically our Sn. And for some points. And so this is roughly the sum over all omega in Pn of omega n. Right? And this is just equal to 1 because this is just a partition of the interval, so this is equal to 1. Sorry, I went very fast at this last bit, but it's all in the notes. And I wanted to also say that, if you develop an intuitive feeling of what bounded distortion means, and the fact that the derivative is roughly constant, then it kind of becomes, the boundedness, so the result that we need, the fact that this is bounded is highly non-trivial, but it is almost an immediate consequence of the bounded distortion according to this very simple argument. Okay? And then you can easily check, and it's in the notes, that it also satisfies this Lipschitz condition. Again, it follows from the bounded distortion. And so that completes the proof of the fact that these here satisfies these conditions here, this boundedness and Lipschitz continuous. And therefore, this implies the same for H, and therefore, this implies the results for the theorem, and therefore, this implies exactly the existence of an absolutely continuous invariant measure, which is ergodic because of the ergodicity of Lebesgue measure. Okay, so this is your first construction, non-trivial construction. So we constructed invariant measures in abstract setting. When you have a continuous map, we just show that this sequence has some limit that is invariant, but here it's a much less trivial map, and we need less trivial arguments. But the result is really quite remarkable, that it means that when you perturb from the piecewise affine case, so you change the slope of the branches, and still you can always find a measure that is invariant, which means you can always find a measure where if you take a little positive measure set and you look at the sum of the branches, they exactly match up to the exact measure of the interval, right? If you think of what you need for the measure to invariant, it's really remarkable that it can exist if it's not the piecewise affine case, but this shows that it can always exist, and in fact, it's Lipschitz continuous density. Okay, I'm sorry that we went late, but it's the last class, so I just wanted to finish this. So thank you very much. So we will still have, I guess you have a couple of tutorials, and you can ask me questions if you have still any questions before the exam. But I've put all the full set of lecture notes now on the online, so you can have a look. And thank you so much. Okay.
Thank you, Professor.
Okay. Thank you. Thank you.